Hi everyone, my name is Vijay Raghavan and I am going to present our paper titled Learn, Unlearn and Relearn, an online learning paradigm for deep neural networks. This is a joint work with Bahram Zunus and Elahe Arani. DNNs deployed in real world are expected to work in an environment where the data arrive in a sequence of large batches. Several learning paradigms have been proposed to learn from a stream of data, including but not limited to continual learning and anytime learning. Although previous efforts established a solid theoretical foundation, certain subtle issues make it inapplicable to the practical environment. For an online learning system, it is important that the learner produces high accuracy and generalizes well at any point in time while using limited computational resources. Recent research in online learning, however, has shown that training from a previously trained model, warm start, rather than fresh initialization, hinders its ability to adapt to its new input, thus incapacitating the generalization of DNNs. A naive approach to mitigate the problem is by retraining the model from scratch each time the new data arrives. However, training the DNNs from scratch each time the new data arrives is computationally inefficient, and the lack of generalization with the warm starting undermines the benefit of training with the learned features. Thus, this problem with the current online learning systems is their inability to generalize across different data streams without sacrificing their previous computations, leading to the lack of efficiency in large-scale deployment of machine learning systems. Motivation. While the DNNs struggle to generalize in an online environment, humans on the other hand learn in succession over lifespan and readily generalize by applying the prior knowledge to novel situations and stimuli without the need to learn from scratch. One such glaring aspect of the brain that allows humans to generalize better is the inherent process of active forgetting. It plays an active role in the regulation of the learning process for better generalizability in the real world. The growing evidence in neuroscience and cognitive psychology suggests that brain actively forgets through selective extension of neurons, which shapes the learning memory process and therefore prevent humans from overfitting to experiences. Thus, emulating this aspect of selective forgetting might hold the key to improving generalizations in DNNs. Anytime learning at macro scale. In this slide, we define the anytime learning settings in which our framework is set up. The ALMA, or the Anytime Learning at Macro Scale framework, is an approach to learning from sequential data. It takes inspiration from both anytime learning and transfer learning. The data is provided to the learner in the form of stream of consecutive batches of samples, referred to as megabadges. The model processes each megabadge, updating its parameter based on the mini batch of examples and aims to minimize its objective function. The model does not have access to the future megabadges and has a limited computational budget. So it has to make a trade-off between effectively generalization and learning from the current data at each megabadge. The model is trained on the current megabadge until convergence, after which it is trained on the next megabadge. ALMA compared to the other learning framework is shown here. In ALMA, megabadges of data are drawn from the same distribution, no drift, and arrive sequentially, but the learner can decide how long to wait before training on them. In the limit, if the learner waits till the end of the stream, then the learning reduces to standard batch supervised training. Thus, in such an online learning settings, we establish our proposed framework to improve generalization. We propose Learn, Unlearn and Relearn, a training paradigm for learning from a sequence of data which interchanges the unlearning and the relearning steps. Our proposed online learning paradigm consists of 3 steps: learn, unlearn and relearn. Our proposed approach is illustrated in the figure. In the first step, the model is trained on the first megabatch of data in anytime learning settings as briefed in the previous slide. Since our main goal is to solve the trade-off between effectively generalization and learning from the current data at each megabatch, we introduce a novel unlearning step in order to improve the performance and generalization of the neural networks. This step selectively forgets the connections that are less relevant for the current data and retains those that are specific to the task. We employ single-shot pruning algorithm for identifying the connections that are less relevant to the current data. For this, we measure the sensitivity of each connections in the network in a data-dependent manner using a subset of data from the current batch. We define a sparsity constraint to determine which connections should be retrained and reinitialized. The top k connections are retained while the rest are unlearned and reinitialized to random values from a uniform distribution. This process of unlearning and relearning is repeated after each megabatch training. And finally, in the relearning step, the network with the new reinitialization is retrained with a new incoming data. The network is trained for the fixed epochs using the cross-entropy laws. The unlearning and the relearning phases are repeated after each megabatch training for effective generalization. Thus, we hypothesize that alternating between unlearning and relearning helps to preserve task-specific connections and improves performance and generalization in DNN. Metrics. For a thorough evaluation, we use cumulative error rate along with test accuracy and generalization gap. To measure the cumulative error rate, we compute the error rate of the model at any instance t using a held out test set. The outer sum computes the discrete integral of the error rate over time. And to determine the generalization gap, we measure the difference between the training and the validation accuracy to understand whether the model is overfitting or underfitting at anytime learning settings. These three measures are used to evaluate the model's generalization and performance. Results. Analysis of short sequence. The results presented in table show the performance of ResNet 18 model trained on three datasets, CIFAR10, CIFAR100 and restricted ImageNet, with and without different forms of reinitialization. The experiment were carried out using 8 megabadges with 6,250 samples each for CIFAR10 and CIFAR100, while 3 megabadges for restricted ImageNet. The results show that reinitialization-based training for online learning consistently improves the test accuracy, cumulative error rate, and generalization compared to the baseline models across all three datasets. It also resulted in the lowest cumulative error rate and generalization gap, and thus improving the model's anytime learning performance. These results suggest that selective forgetting of undesirable information through weight reinitialization and relearning them can bring benefit to the model's learning in online settings. Analysis of short sequence with no replay scenario. Here, we analyze the model's performance under no replay settings. For example, the model is trained on each megabatch only once with no access to the previous megabatches, which makes it challenging. The results of training the ResNet 18 model using the proposed method showed consistent improvements in performance compared to the other baselines across multiple datasets, and it also outperforms them by a significant margin. Thus, training with Lure has a profound impact on online learning in challenging no-replay scenarios. Analysis of moderate and long sequence. The results of the ResNet 18 model trained on CIFAR10 dataset using the Lure framework were compared to the other methods. The experiments were conducted using full replay for varying megabyte sequence of 25, 50 and 100. The results showed that Lure consistently performed better than the other methods, especially for long sequences of megabatches. The model's predictive capabilities were enriched as Lure reduced the cumulative error rate and generalization gap compared to the standard training. Analysis on varying architectures. Here, I would like to talk about the versatility of our proposed Lure framework to multiple architectures on the CIFAR10 dataset. We have tested our framework on popular computer vision models such as ResNet 18, ResNet 50 and wider ResNet and VGG16. In this table, we can clearly see that Lure significantly outperforms standard training across all these architectures, while the other methods such as LLF and Shrink and Pertram fail to improve the performance. This again reinforces that reinitializing the weight parameters in a data-dependent manner as done by Lure is more effective in improving the generalization of different architectures than reinitializing based on the assumed model properties. Analysis of few-shot experiments on restricted ImageNet. In the real-world situations, labeled data may become available gradually, so it is important for the model to work well with limited labeled data. Therefore, we analyze the performance of our proposed Lure framework in a few-shot classification scenario on the restricted ImageNet dataset. We used ResNet 50 as the backbone architecture and the same hyperparameters as in ALMA settings. We varied the number of samples available per class and evaluated the results using the same metric as described previously. The results shown here demonstrate that Lure outperforms the baseline in both settings, achieving the highest accuracy and lowest generalization gap. In conclusion, our proposed approach Lure not only improves generalization in standard settings but also provides better results in challenging few-shot classification compared to the other baselines. Robustness to natural corruptions. Since DNNs are widely deployed in constantly changing environments, the robustness of the DNNs to naturally corrupted data is crucial. Here, we evaluate the effect of Lure on the robustness to common corruptions using the CIFAR10 corrupted dataset. The models were trained on the clean images and tested on the CIFAR-10 corrupted images. The mean corruption accuracy was used to measure their performance. Results showed that, compared to the other methods, Lure achieved higher mean corruption accuracy in all types of corruptions with a result of 74% compared to the baseline of 68%. This highlights the benefit of unlearning and relearning at each megabatch of training for improved robustness to natural corruptions. Robustness to adversarial attacks and noisy labels. Here, we investigated the vulnerability of the deep neural networks to adversarial attacks. We performed a PGT attack of varying strengths on the models trained on CIFAR-10 dataset. Our results, as shown in the figure left, training with Lure framework leads to models that exhibit greater resistance to these attacks compared to the standard training methods. Thus, training a model in the Lure framework helps the model to learn high-level abstractions that are not sensitive to perturbations in the data. Furthermore, to test the sensitivity of the model to noises present in the data, we focus on training the models on noisy labels. We take ResNet 18 and train it on sequential CIFAR-10 dataset with noisy labels in the megabatch sequence of 4. We evaluate the performance on a clean test set. To create noisy labels, we corrupt the ground truth labels with a specific probability. The results show that our reinitialization based training is robust to noisy labels as compared to the worm started baseline. Furthermore, our method Lure outperforms the other baseline across different noisy label rates. This demonstrates that our reinitialization method helps to learn a generic representations that are less sensitive to noises in the dataset. Robustness of connection selection across training steps. In the proposed Lure framework, we selectively forget the least impactful parameters at each megabatch of training by selecting connections. Therefore, it is important to evaluate the consistency of this connection selection across training steps. We conduct a study on the short sequence anytime learning scenario using the ResNet 18 model on the CIFAR-10 dataset. We globally retain 80% of the parameters and reinitialize 20% at the end of each megabatch. To measure the consistency, we save the connection sensitivity mask and calculate the overlap percentage of the retained parameters between the consecutive megabatches. Our results show that the overlap percentage is high in the earlier layers and decreases in the later layers as it learns class-specific information. Although the overlap percentage is lower in the later layers, our method selectively unlearns parameters in the earlier layers depending on the incoming data. Thus, this flexible nature of our method in unlearning and regulating the connections in both early and as well as later layers improves generalization in the anytime settings. And this result is profound across full replay, buffered replay and no replay scenarios. Thus, to conclude, we propose Learn, Unlearn and Relearn, an online training paradigm to improve the performance and generalization of DNNs through the lens of selective forgetting. We demonstrate the efficacy of Lure in multiple convolutional architectures across different datasets in online learning and few-shot classification scenario. Lure exhibits robustness in solving more common challenges in real-world problems, including learning with noisy labels, natural corruption, and adversarial attacks. Finally, Lure is robust to changes in hyperparameters and leads to well-calibrated models. Thank you for listening.